Welcome, dear listener, to this quiet space, a gentle harbour for your mind to rest. Tonight, and in the nights to come, we will embark on a journey together, a slow and peaceful drift through the grandest story of all, a journey through time. We will travel from the very first moment of existence to the silent stillness of this present moment, exploring the science of our universe not as a collection of facts, but as a single, unfolding lullaby. So, find a comfortable position, let the weight of the day begin to dissolve, and allow your breath to be your anchor. Before we begin our story, I would love to know where you are listening from tonight. Feel free to leave a gentle comment below, sharing your city or your country, creating a quiet connection with fellow listeners around the world. And if you find solace in our journey, please consider supporting this channel with a like and a subscription. It helps this quiet corner of the internet to grow. Thank you so much. And now, let us begin. Our story starts before the first star, before the first atom, before even the first ray of light had a space to travel through. It begins in a state of profound and perfect simplicity, a point of existence so dense and so unified that all the laws of the universe, all its future galaxies and worlds and dreams, were held within a space smaller than a single grain of sand. This initial state is what science calls a singularity, but we can imagine it not as a point of fire, but as a silent, sleeping seed of potential. In this state, there was no before, for time itself was woven into its very fabric, waiting to be unfurled. All the forces of nature that govern our world today, the patient pull of gravity that holds the moon in orbit, the electromagnetic force that carries the warmth of sunlight to your skin, and the two nuclear forces that bind the hearts of atoms together, were not separate things, but were instead a single, perfect, harmonious unity. There was no space to measure, no clock to tick, only a state of pure, undifferentiated being, a silent breath held in the heart of nothingness. Imagine all the colours of a grand masterpiece held within a single drop of clear water, all the notes of a symphony contained in a single moment of perfect silence. This was the universe in its first embryonic moment. Then, with an unimaginable grace, that seed of potential began to expand. This was not an explosion in the way we might think of one, a chaotic eruption of fire and sound into a pre-existing emptiness. Rather, it was a gentle and yet impossibly rapid unfurling of space-time itself, a process known as cosmic inflation. Space did not exist for the universe to expand into. Space itself was what was expanding, stretching and swelling from that infinitesimal point in a fraction of a second, carrying all of that primordial energy with it. It was as if a perfectly smooth sheet of silk was being stretched out in all directions at once, its fabric becoming vast and cool and immeasurably large, laying the very groundwork, the vast cosmic stage, upon which all of future history would be written. As space-time expanded, it also cooled, and in this cooling, the perfect unity of the beginning began to differentiate. That single, unified force gently fractured, like crystal forming in cooling water, separating into the four fundamental forces we know today. Gravity was the first to emerge, a subtle, long-reaching whisper that would one day gather the mists of space into stars. Then came the strong nuclear force, the powerful bond that would serve as the heart of all matter, followed by the weak nuclear and electromagnetic forces, each finding its own unique voice, its own distinct role in the emerging symphony of the cosmos. The universe was now filled with a hot, dense, and opaque fog of elementary particles, a vibrant and energetic soup of quarks and electrons and photons, all dancing in a chaotic bath of energy, unable to settle, unable to form anything lasting. It was a universe of pure, raw ingredients, a world still too hot and too young for matter as we know it, a beautiful and formless beginning. This was the universe in its infancy, a glowing, vibrant fog where light was trapped, entangled in an endless dance with matter, a brilliant but featureless cosmos, waiting patiently for the moment it could finally become clear. And so the universe continued its graceful expansion, a silent and ongoing act of becoming, its vibrant, glowing fog of particles stretching and thinning with each passing moment. For hundreds of thousands of years, This state of luminous opacity persisted. The cosmos was filled with light, yet it was a universe without sight, a brilliant whiteout where photons, the very particles of light, could not travel more than a few steps before being absorbed and re-emitted by a charged particle, a free-roaming electron or proton. Imagine trying to see through the densest fog on a bright day. The light is everywhere, yet it reveals nothing, its journey constantly interrupted. This was the state of the young universe, a brilliant but formless haze, a canvas filled entirely with light, awaiting the first brushstroke of structure. Within this cosmic fog, however, the first creative act of matter was already underway. In the first few minutes after the great unfolding, the universe had cooled just enough for the fundamental particles, the quarks and gluons, to bind together, forming the first, most stable atomic nuclei. This process, known as primordial nucleosynthesis, was the universe's first foray into chemistry, a delicate dance of temperature and density that forged the nuclei of the lightest elements. An overwhelming abundance of hydrogen, the simplest element of all, with its single proton, a smaller amount of helium, and trace amounts of lithium. These were the raw materials from which all future complexity would be built, the elemental building blocks for every star, every planet, and every living being that would ever emerge. Yet, for now, they remained as bare nuclei, adrift in a sea of frantic electrons, their positive charge preventing them from capturing these electrons to become stable, neutral atoms. For 380,000 years, this cosmic dance continued, a slow, patient cooling as space continued to expand. Then, the universe reached a tipping point, a moment of profound transformation. The temperature dropped to roughly 3,000 degrees Kelvin, a threshold cool enough for the protons and helium nuclei to finally capture the free-roaming electrons, their opposite charges drawing them into stable, gentle orbits. This moment is known as the era of recombination. It was not a sudden event, but a gradual settling, like steam slowly condensing into water. As electrons found their homes, bound to atomic nuclei, the universe underwent a miraculous change. For the first time, it became electrically neutral. And because photons no longer scattered off of free-floating charged particles, the fog suddenly, beautifully, cleared. Light was set free. The universe, in an instant of cosmic grace, became transparent. The light that was present at that very moment, the photons that were in the middle of their journey when recombination occurred, were now free to travel unimpeded across the vast, expanding canvas of space. They have been traveling ever since, their wavelengths stretched by the expansion of the universe over billions of years, cooling from a brilliant, visible glow into the faint, invisible energy of microwaves. This ancient light, this first glimmer of a transparent cosmos, is still all around us today. We call it the cosmic microwave background, or the CMB, and it is the oldest light in existence, a fossil echo of the universe's first dawn. When we map this faint, gentle glow across the sky, we are looking at a snapshot of the universe as it was over 13.8 billion years ago. A baby picture of the cosmos, its light finally reaching us after a journey across the entire expanse of space-time. This whisper of radiation is not perfectly uniform. It has tiny, almost imperceptible variations in temperature, gentle ripples of slightly denser and slightly less dense regions in that primordial haze. These subtle fluctuations were the seeds, planted by gravity, from which all future structures would grow, the faint outlines of the great cosmic web of galaxies that would one day fill the vast and silent dark. Within that vast and newly transparent darkness, the seeds of all future light and warmth lay dormant, scattered like a fine dust throughout the endless night. These were the gentle ripples in the fabric of the early cosmos, the almost imperceptible regions where the primordial gas of hydrogen and helium was just a fraction denser than the space surrounding it. For millions of years, the universe remained a dark and silent expanse, a kingdom of gas clouds drifting patiently in the cold. But a quiet and persistent force was already at work, a gentle whisper that had been present since the very first moments of existence. This force was gravity. It is often imagined as a commanding pull, a power that dictates the fall of an apple or the orbit of a planet, but in these early days, it was more like a patient invitation, a subtle, cumulative coaxing of matter into communion. Across unimaginable distances and over eons of time, gravity began to draw the scattered atoms of hydrogen and helium towards those slightly denser regions. The process was impossibly slow, a cosmic ballet choreographed on a scale of millions of years. It was not a rush, but a gentle, spiraling drift. As countless individual atoms, each with its own tiny gravitational signature, began to answer the call of the collective, great, ethereal clouds of gas, which we now call nebulae, began to form, their edges blurring into the vacuum of space, their hearts slowly growing thicker and warmer. Imagine a wisp of breath on a cold day, its molecules swirling and condensing into a visible cloud. Now imagine that cloud spanning light years, its substance, the very building blocks of the universe, its formation taking not a second, but an eternity. As these clouds grew, their own gravity increased, pulling in more and more material from their surroundings. A gentle feedback loop began. The more massive the cloud became, the stronger its gravitational pull, and the faster it could gather even more gas. Deep within the hearts of the densest nebulae, clumps of matter began to form, spinning slowly as they contracted, like water circling a drain. These spinning cores are known as protostars, the embryonic stage of a star's life. As the material fell inward, immense pressure began to build at the center, and the temperature soared, climbing through thousands, and then millions, of degrees. The protostar began to glow, not with the fire of fusion, but with the simple heat of compression, a dull red ember shining faintly from within its shroud of gas and dust. For millions of years, this process of contraction and heating continued, the protostar's core becoming ever denser, ever hotter, until it reached a critical threshold. At a temperature of around 15 million degrees Celsius, the pressure at the core became so immense that it could overcome the natural repulsion between atomic nuclei. The universe was about to witness its greatest miracle. Hydrogen nuclei, the simplest atoms in existence, were forced together with such power that they fused, merging to form the next simplest element, helium. In this act of nuclear fusion, a tiny amount of mass was converted into a tremendous burst of energy. According to Einstein's famous equation, E equals mc squared. This outward rush of energy finally balanced the inward crush of gravity, stabilizing the core and halting its collapse. A star was born. A self-sustaining, light-producing engine had been ignited in the cosmic dark. The universe, after millions of years of darkness, had lit its first candle, and then another, and then billions upon billions more, until the night sky was no longer empty, but woven through with the soft, distant light of the first stellar nurseries. The first stars to grace the universal night were not like the familiar, gentle sun that warms our own world. Born from the pure, unadulterated hydrogen and helium of the early cosmos, they were titans, hundreds of times more massive than our sun, and they lived lives that were correspondingly brilliant, violent, and astonishingly brief. They burned with a fierce, blue-white intensity, pouring unimaginable amounts of energy out into the void, their light so powerful it could illuminate entire nascent galaxies. But this brilliance came at a cost. Like a great fire consuming its fuel at a furious pace, these massive stars burned through their vast reserves of hydrogen in only a few million years, a mere cosmic heartbeat compared to the 10 billion-year lifespan of a star like our Sun. As a star's life unfolds, its core becomes a crucible, a cosmic forge where new elements are created. Once the hydrogen in the core is exhausted, having been fused into helium, the star's engine begins to sputter. Gravity once again gains the upper hand, compressing the core further, raising the temperature and pressure to even more extreme levels. A new threshold is crossed, and the star begins to fuse the helium atoms themselves, forcing three of them together to create a new element, carbon. This is a moment of profound significance in our journey, for carbon is the backbone of all known life, the versatile atom upon which the complex molecules of biology are built. The star has now become like a cosmic onion, with a core of fusing helium surrounded by a shell of fusing hydrogen. As the star continues to age, this process repeats. When the helium is depleted, the core contracts again, becoming hotter still, and begins to fuse carbon into heavier elements like oxygen and neon. This layering continues, forging magnesium, silicon, and sulfur, each new element created in the heart of a dying star, a testament to the creative power of immense pressure and heat. This process of stellar nucleosynthesis continues until the star's core is composed of iron. Here, the journey of creation within the star reaches its end. For all the elements leading up to iron, the process of fusion releases energy, pushing back against gravity's relentless crush. But fusing iron nuclei does not release energy. It consumes it. The star's internal furnace is extinguished. In less than a second, the delicate balance that has sustained the star for millions of years is shattered. With its energy source gone, there is nothing to oppose the force of gravity, and the star's core collapses catastrophically upon itself. The outer layers of the star, now unsupported, come rushing inward at a fraction of the speed of light, slamming into the impossibly dense, collapsed core. The result is a rebound of unimaginable power, an explosion that tears the star apart in an event known as a supernova. For a few brief weeks, this single exploding star can outshine its entire host galaxy, blazing with the light of 100 billion suns. But this is more than just a destructive event. It is the ultimate act of cosmic generosity. The immense energies of the supernova itself forge all the elements heavier than iron: the copper, the silver, the gold, the mercury, the lead, the uranium. Every element that makes our world rich and complex is born in this final, violent moment. And in that magnificent explosion, all the elements the star has spent its life, creating the carbon, the oxygen, the silicon, the iron, and all the newly minted heavy elements are cast out into space at incredible speeds, seeding the surrounding interstellar clouds with the raw materials for new creation. The ashes of these first dying suns enriched the universe, making the next generation of stars and planets fundamentally different and infinitely more capable of complexity. Our journey through time is a story of cycles, and here we see the most profound one of all. For new worlds to be born, for life itself to become possible, the first stars had to die. Out of the generous ashes of those first dying suns, new clouds of gas and dust began to gather, drifting through the arms of a young and spiraling galaxy we now call the Milky Way. These were not the simple, pristine clouds from which the first stars were born. They were cosmic nurseries, enriched with a profound inheritance, seeded with the carbon, oxygen, silicon, and iron that had been forged in stellar hearts and scattered by supernovae. This was the legacy of the universe's first generation, a gift of complexity that made a world like ours possible. About 4.6 billion years ago, in a quiet, unremarkable corner of this galaxy, one such cloud began its slow and patient collapse. Just as before, gravity was the silent choreographer, gently coaxing the swirling material inward. At the heart of this spinning disk of matter, which we call a solar nebula, the pressure and temperature once again climbed to the point of ignition, and a new, second-generation star was born, our Sun. But the story of the material surrounding this newborn star was different now. While the vast majority of the hydrogen and helium was drawn into the Sun, a flattened, spinning disk of heavier material remained in orbit, a vast protoplanetary disk stretching out for billions of miles. Within this disk, a new kind of creation began, not through the grand fire of fusion, but through a slow, gentle, and persistent accumulation. Tiny dust grains, fragments of carbon and silicates, no larger than particles of smoke, began to drift and collide. Held together by faint electrostatic forces, they formed fluffy aggregates, which in turn collided to form larger bodies. This patient process, known as accretion, continued for millions of years, building matter from the microscopic to the macroscopic. Pebbles grew into boulders, boulders grew into mountains, and these mountain-sized bodies, called planetesimals, began to exert their own significant gravitational pull, sweeping up the remaining material in their orbits. In the inner part of the solar system, where it was warmer, the rocky planets formed: Mercury, Venus, Mars, and our own Earth. In its earliest days, the Earth was a molten world, a sphere of glowing rock heated by the constant impacts of accretion and the decay of radioactive elements in its core. It was a hellish and inhospitable place, its surface a shifting ocean of lava. But even in this fiery beginning, the seeds of a future sanctuary were being planted. During a period known as the Late Heavy Bombardment, the inner solar system was pelted by a final flurry of asteroids and comets, remnants of its chaotic formation. These icy visitors, hailing from the cold outer reaches of the solar system, were cosmic messengers carrying a precious cargo: frozen water. Impact after impact, they delivered this water to the hot surface of the young Earth, where it turned to steam and shrouded the planet in a thick, dense atmosphere. As the planet slowly began to cool over millions of years, this steam condensed and fell as rain, a deluge that lasted for millennia, filling the basins and craters to form the first vast global oceans. And in this early, formative era, one last grand event would shape our world's destiny. A protoplanet, roughly the size of Mars, is thought to have collided with the young Earth in a glancing blow. This immense impact threw a vast cloud of molten rock and debris into orbit, which then slowly coalesced under its own gravity to form our moon. The moon's presence has been a gift of profound stability, its gentle gravitational pull acting like a steadying hand on our planet, preventing it from wobbling wildly on its axis, and thus creating the predictable seasons and the stable, gentle climate that have allowed life to flourish. And so, the stage was set. A rocky planet, gifted with the elements of dead stars, blessed with oceans of water from the far reaches of the solar system, and held in a steady, gentle rhythm by its celestial companion. Our world was no longer a sphere of fire, but a pale blue cradle, floating in the silent dark, waiting for a new kind of story to begin. And so our pale blue cradle drifted through the silent cosmos, its fiery birth giving way to a long and quiet infancy. Imagine this young Earth, a world of water under a thick, hazy atmosphere of nitrogen, carbon dioxide, and methane, tinged orange by a faint, young sun. The continents we know had not yet formed, and the vast, planet-spanning ocean was a sterile and silent expanse, rich with dissolved minerals but empty of life. It was a world of profound potential, a perfectly prepared canvas, waiting for the first touch of the artist's brush. Within these warm primordial waters, a new kind of evolution was beginning, not yet biological, but chemical. The ocean was a vast chemical laboratory, a primordial soup containing simple organic molecules, the building blocks of life. Some of these molecules, like amino acids and nucleotides, may have been delivered to Earth by the same comets and meteorites that brought the water, forged in the cold chemistry of interstellar space. Others may have been synthesized right here, in the atmosphere, by the energetic spark of lightning crackling through the dense clouds, or in the deep, dark places of the ocean floor. Here, at hydrothermal vents, plumes of hot, mineral-rich water billowed up from the planet's interior, creating chemical gradients of energy and temperature, like warm oases in the cold, abyssal dark. In these gentle, energy-rich environments, a quiet miracle was unfolding. Simple molecules began to link together, forming longer, more complex chains called polymers. This process, known as abiogenesis, is the story of how non-living matter gave rise to life. It was not a single, instantaneous event, but a slow, patient series of countless tiny steps, a gradual increase in complexity over millions of years, driven by the simple laws of chemistry and physics. Among the countless molecules being formed, one type emerged that was truly special. It was a long, chain-like molecule called ribonucleic acid, or RNA. In our modern world, RNA is often seen as a simple messenger, carrying instructions from the master blueprint of DNA to the cell's protein-building machinery. But many scientists believe that in the early days of life, RNA played all the major roles itself. This is the RNA world hypothesis. This remarkable molecule could not only store information in the sequence of its chemical letters, much like DNA does, but it could also fold itself into complex three-dimensional shapes that could act as enzymes, catalyzing chemical reactions, including, most crucially, the reaction to make copies of itself. Imagine a single, microscopic thread, a strand of information floating in the ancient sea that had the magical ability to build another version of itself from the raw materials floating around it. This was the dawn of replication, the birth of heredity. It was the moment the universe developed a memory. These first, self-replicating strands of RNA were fragile, at the mercy of the open ocean. The next crucial step was the formation of a container, a boundary that could protect these precious molecules and concentrate them together with the resources they needed to copy themselves. This boundary came in the form of simple, fatty molecules called lipids, which naturally arrange themselves into hollow spheres, or bubbles, when in water. These were the first protocells. They were not yet truly alive, but they were the precursors to life, a simple membrane separating an internal, organized chemistry from the chaos of the outside world. This was the first self. Inside these tiny, protective bubbles, the ocean's first dream of life began to stir. A quiet, fragile process of replication and selection, a new kind of story beginning to write itself in the silent depths of a young and waiting world. For over 1 billion years, life remained a quiet and hidden affair, a story written in the microscopic script of single-celled organisms thriving in the planet's dark and oxygen-free corners. These first life forms, the simple prokaryotic cells like bacteria and archaea, drew their energy not from the sun, but from the rich chemical broth of the deep-sea vents, or the minerals dissolved in the rock around them. The sunlit surface of the vast global ocean was a shimmering desert, a place of abundant energy that life had not yet learned how to harvest. But life is an endless experiment, a relentless exploration of the possible. And in the warm, shallow waters of the ancient world, a new kind of microbe was evolving, a revolutionary skill. These were the cyanobacteria, and the miracle they mastered was photosynthesis. They developed a remarkable molecular machine, a pigment called chlorophyll, which could capture the energy of a single photon of sunlight. It was a clever and elegant trick, a way to tap into the inexhaustible power of our star. The process was a form of alchemy. The cyanobacteria would take in the carbon dioxide, or CO2, that was abundant in the atmosphere, and they would draw in water, or H2O, from the ocean around them. Using the energy captured from sunlight, they broke the water molecules apart and rearranged the atoms to create simple sugars to fuel their own growth. It was a perfect, self-sustaining cycle, a way for life to weave light into matter. But this elegant process produced a byproduct, a waste gas that was expelled into the water. This waste product was oxygen. For the first few 100 million years, this newly produced oxygen did not build up in the atmosphere. Instead, it was immediately absorbed by the vast amounts of dissolved iron in the oceans, a legacy of the planet's formation. As the oxygen reacted with the iron, it caused it to rust, precipitating out of the water and sinking to the seafloor in vast, rust-colored layers. Over eons, this process created the immense geological formations we now call banded iron, a silent, striped testament in the rock, telling the story of the planet slowly rusting. But eventually, after countless generations of cyanobacteria had lived and died, after the oceans had given up all the iron they could, the sinks became full. The oxygen had nowhere else to go. And so, beginning around 2.4 billion years ago, it started to bubble out of the oceans and pour into the sky, beginning a process that would forever change the face of our world. The Great Oxidation Event. For the existing anaerobic life that had thrived in an oxygen-free world, this new gas was a deadly poison, and the change triggered the planet's first great extinction. But for life as a whole, it was a moment of profound transformation. The hazy, methane-rich orange sky began to clear, turning a brilliant blue. The oceans, once a murky olive green from dissolved iron, became clear and transparent. And high up in the stratosphere, the newly abundant oxygen, or O2, was struck by the sun's ultraviolet radiation, its molecules splitting and reforming into a new configuration with 3 atoms instead of 2. Ozone, or O3. This ozone layer began to form a protective shield around the planet, absorbing the most harmful solar radiation, which until then had relentlessly sterilized the surface. The planet was taking its first deep, cleansing breath, a breath that would make the land habitable and pave the way for a new, more energetic and more complex kind of life to finally emerge from the shadows. With the world now bathed in the gentle blue light of a clear sky and the oceans rich with life-giving oxygen, the stage was set for an evolutionary leap of breathtaking complexity. For nearly 2 billion years, life had been the exclusive domain of simple prokaryotic cells, tiny, efficient survival machines without a nucleus or any specialized internal structures. But this new, oxygen-rich environment was a playground of energetic potential, and it favored a new kind of cellular architecture. The next great chapter in our story began not with competition, but with an act of ancient and profound cooperation. A larger, more complex cell is thought to have engulfed a smaller, simpler bacterium. But instead of digesting it, the two entered into a permanent partnership, a symbiosis that would change the future of life. The smaller bacterium, which was particularly adept at using oxygen to produce energy, became the ancestor of what we now call mitochondria, the powerhouses that fuel every complex cell, including our own. This new composite organism was the first eukaryotic cell. It was a masterpiece of biological engineering, a vast and bustling city compared to the simple tent of the prokaryote. It contained a central nucleus to protect its precious genetic blueprint, and an entire suite of specialized compartments, or organelles, to handle everything from protein production to waste disposal. This new cellular design was a revolution, providing the stability and energetic surplus needed to experiment with an entirely new way of being, multicellularity. For the first time, cells began to cling together after dividing, forming simple colonies. And within these colonies, they began to communicate, to cooperate, and to specialize. Some cells might become responsible for movement, others for feeding, and still others for reproduction. This division of labor allowed for the creation of larger, more complex body plans than any single cell could ever achieve on its own. For hundreds of millions of years, these new multicellular organisms remained simple, consisting of soft-bodied, plant-like fronds and strange, quilted patterns that lay on the dim sea floor, a quiet and enigmatic kingdom known as the Ediacaran biota. Then, around 541 million years ago, in the geological blink of an eye, the quiet garden of the silent seas erupted into a riot of innovation. This period, known as the Cambrian explosion, was a time of unprecedented evolutionary creativity, when almost all the major animal body plans that exist today first appeared. The oceans, once home only to gentle, slow-moving organisms, were suddenly filled with a dazzling array of new creatures. Animals evolved the first hard shells and exoskeletons for protection and support, giving rise to the iconic, armored trilobites that scuttled across the seabed. The first true predators emerged, like the formidable Anomalocaris, with its large, grasping claws and circular jaw. And perhaps most momentously of all, life evolved a new way to sense the world. Vision. The first complex, image-forming eyes appeared, and for the first time, the universe could be seen with clarity and detail. The world was no longer just a collection of chemical gradients and vague shadows. It was a vibrant tapestry of shapes and forms and movements. This new sense transformed the relationship between organisms, creating a dynamic dance of hunter and hunted, of seeing and being seen. The silent seas were now a complex and interactive ecosystem, a garden of strange and beautiful forms, where life was not just surviving, but actively perceiving, exploring, and shaping its world in a way it never had before. For hundreds of millions of years, life's grand and vibrant story had been an exclusively aquatic epic, its chapters written in the silent, sunlit gardens and the dark, mysterious depths of the sea. The continents, meanwhile, were a vast and silent emptiness, landscapes of barren rock and sterile soil baked under the unfiltered glare of the sun. But the land offered a profound invitation: direct access to sunlight, an atmosphere rich in carbon dioxide, and a world free from predators. It was a frontier of immense opportunity, waiting for the first courageous pioneers to leave the familiar comfort of the water. The first to answer this call were not animals, but the humble plants. Simple green algae, thriving in the shallow coastal fringes and freshwater ponds, began to creep up onto the damp rocks, forming a green film over the sterile landscape. To survive in this new and hostile world, they had to overcome immense challenges. The air threatened to dry them out, so they evolved waxy outer coatings to seal in their precious water. Gravity, a force barely felt in the buoyant embrace of the ocean, now threatened to pull them down, so they developed rigid cellular structures and eventually stems to hold themselves up towards the light. These first small, non-vascular plants, like the mosses and liverworts we see today, clung close to the ground, creating the first patches of living green on the empty continents. They were the architects of the land, their simple root-like structures breaking down the rock, their decaying bodies creating the first true soil. They began to change the very character of the planet, laying the foundation for a richer and more complex terrestrial world. Following the plants, the first animals ventured ashore. Arthropods, creatures already equipped with a supportive exoskeleton, were among the first, with ancient relatives of millipedes and insects exploring this new, greening landscape. But the most momentous journey was yet to be made. In the shallow, murky waters of the Devonian period, a group of lobe-finned fishes were uniquely prepared for the transition. These fish lived in environments that often dried up or were low in oxygen, so they had evolved not only gills to breathe in water, but also a primitive lung to gulp air from the surface. And their fins were not the delicate, papery structures of most fish. They were thick and muscular, supported by a sturdy arrangement of bones, remarkably similar to the bones in our own limbs. Over countless generations, these powerful fins became more and more like legs. We can see this beautiful transition in fossils like Tiktaalik, a creature with the scales, fins, and gills of a fish, but with the flattened skull, mobile neck, and robust limb bones of a land animal. It could prop itself up in the shallows and, perhaps, make short, shuffling journeys across the mudflats. This was the tentative first step of a vertebrate on land. Imagine the sensory world of that first explorer. The sudden, immense weight of its own body under the full force of gravity, the air, so much thinner than water, rushing into its lungs, the new, rich smells of damp earth and decaying plants. Slowly, these pioneering amphibians grew more confident on land, their limbs becoming stronger, their lungs more efficient. They gave rise to a world teeming with new life, and by the Carboniferous period, the planet was covered in vast, steamy, tropical swamp forests of giant ferns, club mosses, and horsetails, a world buzzing with the sound of giant dragonflies and inhabited by sprawling amphibians in the humid undergrowth. The land was no longer silent. It was whispering with the rustle of leaves and the gentle movements of its new inhabitants. The lush, damp world of the Carboniferous forests, with its giant insects and sprawling amphibians, eventually gave way to a drier and warmer climate. As the planet's great landmasses drifted together to form the single, immense supercontinent of Pangaea, the extensive swamps retreated, and a new kind of animal, better adapted to these drier conditions, rose to prominence. These were the reptiles, whose scaly skin and amniotic egg, a self-contained, private pond for their developing young, freed them from their dependence on the water's edge and allowed them to conquer the vast continental interiors. From this reptilian stock, a truly extraordinary dynasty would emerge, a group of animals that would rule the earth for a period of time that dwarfs the entirety of human history. This was the beginning of the Mesozoic era, the great age of dinosaurs. For over 150 million years, these creatures were the undisputed masters of the terrestrial world, and they diversified into a breathtaking array of forms, a testament to the creative power of evolution. Our modern imagination often paints them as terrifying monsters, but it is perhaps more profound to see them as a story of immense and enduring success. Imagine the world they inhabited, a world so different from our own, with its strange vegetation of ferns, cycads, and conifers, under a sky that had more oxygen than our own. Picture the gentle majesty of a herd of long-necked sauropods, creatures like Brachiosaurus, their heads reaching high into the canopies of the trees, their immense bodies moving with a slow and graceful rhythm. Envision a vast open fern prairie, where a family of armored triceratops, with their three-horned faces and great bony frills, grazed peacefully. Their young nestled safely in the center of the herd. Think of the intricate social behaviors, the nesting grounds, where Maiasaura, the good mother lizard, carefully tended to its eggs and cared for its hatchlings. See the feathered dinosaurs, the ancestors of modern birds, covered in plumage not yet for flight, but perhaps for warmth or for vibrant display, hinting at a world of rich color and complex communication. As the long millennia of their reign unfolded, the supercontinent of Pangaea slowly began to break apart, the continents drifting towards their modern positions, creating new oceans and changing global climates, and the dinosaurs adapted and evolved in response. Their story one of constant change and resilience. Their long reign created a sense of permanence, as if their kingdom might last forever. But the universe is a place of cycles, and even the greatest dynasties must eventually come to an end. 66 million years ago, a silent traveler from the outer reaches of the solar system, an asteroid or comet some 10 kilometers wide, ended its long journey through space. It struck the Earth in the shallow waters of what is now the Gulf of Mexico, with an energy of billions of atomic bombs. The impact triggered a global catastrophe, sending a cloud of superheated dust and ash into the atmosphere that shrouded the planet in darkness, causing temperatures to plummet and plants to wither and die. The long, vibrant, sun-drenched day of the dinosaurs drew to a sudden and dramatic close, their magnificent story not ending in a slow fade, but in a final, dramatic turning of the page, making way for a new and different kind of world to emerge from the quiet twilight. In the quiet, grey twilight that settled over the Earth after the Great Impact, a new world began to take shape from the ruins of the old. The long and sunlit reign of the giants was over, and the planet's vast ecosystems lay empty, waiting for new inheritors. For over 100 million years, while the dinosaurs had walked the Earth in the full light of day, a different kind of creature had been quietly thriving in the shadows. These were the first mammals, small, nocturnal, and often no larger than a modern shrew, scurrying through the prehistoric undergrowth, navigating a world defined by the senses of smell and sound. They had lived their lives at the feet of the giants, in a state of perpetual caution, a footnote in a story that was not their own. But the very traits that had kept them small and hidden were the keys to their survival. Their small size meant they needed far less food to survive in the lean, post-impact world. Their warm-blooded nature, a state of being known as endothermy, allowed them to carry a constant, internal fire, a private warmth that made them resilient to the plunging global temperatures and enabled them to remain active in the cold and the dark. Many were burrowing creatures, and their subterranean dens offered shelter from the worst of the initial catastrophe. While the great reptilian herbivores starved as the plants withered, these small mammals survived on the resilient bounty of the forest floor. Insects, worms, seeds, and roots. The world had been emptied, and it was these humble, resourceful survivors who would emerge from the shadows to claim it. This was the dawn of the Cenozoic era, the age of mammals. With the great dinosaurs gone, a vast landscape of ecological opportunities, or niches, was now vacant. What followed was a remarkable evolutionary flourishing known as an adaptive radiation. From those small, shrew-like ancestors, mammals exploded in diversity, evolving over millions of years to fill every role the dinosaurs had left behind, and inventing new ones entirely. Some returned to the sea, their limbs transforming into flippers, becoming the ancestors of whales and dolphins. Others took to the air, their forelimbs evolving into wings, becoming the first and only mammals capable of true flight. The bats. On the land, they became the new grazers and browsers, the new hunters and scavengers, growing in size and complexity, their forms diversifying into the familiar shapes of horses, elephants, cats, and bears. And they brought with them a new and gentle evolutionary strategy. Instead of laying many eggs and leaving their young to fend for themselves, they invested deeply in just a few offspring, nourishing them first within the body, and then after birth with milk, a process called lactation. This extended period of parental care created a powerful bond between mother and child, and it created a space for learning, for the transmission of complex behaviors from one generation to the next. The world was no longer governed solely by instinct, but increasingly by intelligence and social connection. Among this great diversification, one group of mammals found its home in the canopies of the emerging tropical forests. These were the primates. Life in the trees demanded a new set of skills. Grasping hands and feet to hold onto branches, and keen, forward-facing eyes to judge distances with precision, creating a rich, three-dimensional, stereoscopic view of the world. This arboreal life set the stage for a new kind of mind, one that saw the world not just as a flat landscape, but as a complex, interconnected web of pathways and possibilities, a world that needed to be navigated with intelligence and foresight. From the lush, three-dimensional world of the forest canopy, our story now turns inward, from the evolution of bodies to the evolution of a mind capable of contemplating its own existence. A lineage of these tree-dwelling primates, our distant ancestors, was forced to adapt to a changing world as the climate cooled and the great forests of Africa gave way to open, sprawling savannas. This new environment, with its vast horizons and scattered resources, favored a radical new posture, walking upright on two legs. This adaptation, known as bipedalism, was a profound turning point. It raised our ancestors' eyes above the tall grasses, allowing them to see both predators and opportunities from afar. But most crucially, it freed the hands. For the first time in our lineage, the hands were liberated from the demands of locomotion, free to carry food, to care for young, and to explore the world with a new and intimate touch. And they began to use tools. At first, it was simple opportunism, picking up a rock to break open a nut, or a sharp stick to dig for roots. But over time, a cognitive leap occurred. An early hominid looked at a piece of flint, and in its mind's eye saw not just a rock, but the potential for a tool sleeping within it. With deliberate and skillful strikes, they began to shape these rocks, creating sharpened edges for cutting and scraping, an act of transforming the natural world to suit their imagination. This interplay between the hand and the mind, between tool use and problem solving, created a powerful feedback loop that drove the expansion of the brain. Over the next few million years, the hominid brain, and in particular its wrinkled outer layer called the neocortex, grew at a rate unprecedented in the history of life. It was not just an increase in size, but a rewiring of its internal connections, an immense increase in its complexity. And from this burgeoning complexity, something entirely new began to emerge: symbolic thought. This was the ability to let one thing stand for another, to think about things that were not immediately present, to imagine the past, and to plan for the future. We see the ghost of this awakening in the archaeological record. The first deliberate burials, suggesting a nascent awareness of mortality and perhaps an inkling of an afterlife. The first personal ornaments, like beads made of shells, suggesting a new sense of individual identity. And then, beginning perhaps around 40,000 years ago, this inner world erupted into the outer world in a breathtaking display. In caves across Europe, these early modern humans used charcoal and mineral pigments to paint the walls, with stunning images of the animals that shared their world: bison, horses, mammoths, and lions. This was more than just decoration. It was the projection of the mind onto stone, the birth of art, an attempt to capture the spirit and the memory of their world. Flowing alongside this was the development of the final, crucial piece: complex language. With a sophisticated grammar and syntax, humans could now share their intricate inner worlds with one another. They could communicate complex ideas, make detailed plans, and, most importantly, tell stories. This cognitive revolution created a new kind of inheritance, not of genes, but of culture. Knowledge and beliefs could now be passed down through the generations, creating a shared reality, a collective consciousness. Inside the human skull, a new kind of universe had been born, an inner sky as vast and as mysterious as the one above, a space of awareness where the cosmos, after 14 billion years of silent, unthinking evolution, had finally awakened and begun to wonder about itself. With this new and luminous inner sky awakened within the human mind, our ancestors began to look up at the vast, dark canopy of the night with new eyes. For the first time, They saw not just a random scattering of distant lights, but a canvas for their imagination, a place to find meaning and to tell the story of their own existence. The silent, predictable procession of the stars, the gentle waxing and waning of the moon, and the wandering paths of the planets became a celestial clock and a calendar, marking the passage of the seasons and the rhythm of their lives. But more than that, the night sky became the first great storybook of humanity. In the patterns of the stars, they saw the outlines of their heroes, their gods, and the creatures of their myths. They connected the distant points of light to create the constellations, projecting their earthly hopes and fears onto the cosmos, and in doing so, they transformed a vast and impersonal universe into a familiar, intimate, and meaningful home. This was the first astronomy, an astronomy of the heart, an attempt to weave the human story into the grander tapestry of the night. As human societies grew more complex, so too did their models of the universe. The philosophers and astronomers of ancient Greece, in their search for a more rational order, developed a beautiful and intricate picture of the cosmos. In the model perfected by the great astronomer Ptolemy, the Earth was seen as the stationary and sacred center of all creation. Around it, in a series of perfect, crystalline spheres, revolved the moon, the sun, and the 5 known planets, with the distant stars fixed to the outermost sphere. This geocentric universe was a place of profound order and hierarchy, a cosmic architecture that reflected a deep-seated human intuition that our world, and by extension ourselves, must be the focus of the universal drama. For over 1,000 years, this elegant vision held sway, a comforting and intellectually satisfying picture of our place in the cosmos. But the universe is always more subtle than our grandest theories. In the 16th century, a quiet Polish astronomer named Nicolaus Copernicus, after a lifetime of patient observation and calculation, proposed a radical and deeply unsettling new idea. He suggested that the Earth was not the center of the universe, but was in fact just another planet, and that all the planets, including our own, were in orbit around the Sun. This heliocentric model demoted humanity from the center of creation to the inhabitants of a peripheral world, a profound shift in perspective that took over a century to be fully accepted. The definitive evidence came from the work of the Italian scientist Galileo Galilei, who, in the early 17th century, turned the newly invented telescope towards the heavens. What he saw shattered the old world forever. He saw that the moon was not a perfect ethereal orb, but a rocky, cratered world, much like the Earth. He saw the moons of Jupiter, a miniature solar system proving that not everything orbited our planet. He saw the phases of Venus, which could only be explained if Venus circled the Sun. The heavens were not a separate, divine realm, but a physical place, subject to the same laws as the Earth. The culmination of this revolution came with the work of Isaac Newton, who, in a single, elegant theory, united the heavens and the Earth. His law of universal gravitation revealed that the same force that causes an apple to fall from a tree is the very same force that holds the moon in its orbit and keeps the planets in their paths around the Sun. The universe, in Newton's vision, was a vast and magnificent clockwork machine, governed by precise, universal, and knowable laws, a cosmos of sublime and predictable order. For 2 centuries, the image of Newton's clockwork universe brought a sense of profound comfort and understanding to the human mind. The cosmos was a grand and logical place, where space was a fixed and absolute stage, and time was a universal river, flowing at the same steady rate for everyone and everything, everywhere. This was a reality that made intuitive sense, a world that matched our everyday experience. But at the beginning of the 20th century, a young patent clerk in Switzerland, named Albert Einstein, a man who spent his days dreaming about the deepest nature of reality, began to gently unravel this tidy and comforting picture. He was troubled by a deep inconsistency between Newton's laws of motion and the known laws of electricity and magnetism, particularly as they related to the nature of light. His profound meditations led him to a revolutionary new understanding of space and time itself, a theory he called special relativity. It was built on 2 simple but world-altering ideas. The first was that the laws of physics should appear the same to all observers who are moving at a constant speed. The second, and far stranger, idea was that the speed of light in a vacuum is constant for every single observer, regardless of how fast they themselves are moving. This seemingly simple statement leads to the most bizarre and counterintuitive consequences. For the speed of light to remain constant for everyone, something else that we consider absolute must be flexible. And that something is time. Einstein realized that time itself can flow at different rates for different observers. For a person moving at a very high speed, time would pass more slowly than for a person at rest. This effect, known as time dilation, means that there is no single, universal clock ticking for the cosmos. Every observer carries their own personal clock, and its rhythm depends on their motion. Space, too, is relative, contracting in the direction of motion. Time and space were no longer a static background, but were instead dynamic and malleable, woven together into a single, unified entity. A four-dimensional fabric called space-time. But Einstein knew his work was not yet complete, for his theory did not include gravity. Over the next decade, he wrestled with this problem, finally emerging with his masterpiece, the theory of general relativity. In this breathtaking vision, gravity is not a force that pulls across distances, as Newton had imagined. Instead, gravity is the very shape of space-time itself. He asked us to imagine space-time as a vast, flexible sheet of rubber. A massive object, like the sun, placed on this sheet, would create a deep dimple, a curvature in the fabric. A smaller object, like the Earth, rolling nearby, is not being pulled by the sun, but is simply following the straightest possible path through that curved space-time, a path that we perceive as an orbit. Mass tells space-time how to curve, and the curvature of space-time tells matter how to move. It is a beautiful, silent dance between matter and the geometry of the cosmos. This radical idea was confirmed during a solar eclipse in 1919, when astronomers observed that the light from distant stars was bent as it passed by the sun, its path following the curve in space-time, exactly as Einstein had predicted. The universe was not a clockwork machine after all, but something far more organic, fluid, and mysterious. A place where space can bend and time can stretch, a reality far stranger and more wonderful than our senses could ever have led us to believe. Just as Albert Einstein revealed that the grand stage of the cosmos was not a rigid and absolute structure, but a fluid and dynamic fabric, a new generation of scientists in the early 20th century was discovering that the very substance of reality, the world of the impossibly small, was even stranger and more mysterious. Their journey into the heart of the atom revealed a world that defied all common sense, a realm that operates on a completely different set of rules from the familiar, solid world of our perceptions. This is the world of quantum mechanics, and it is not a place of solid, definite things, but a place of potential, probability, and profound interconnectedness. At the foundation of this strange new world is the discovery that the elementary particles that make up everything, the electrons and photons and quarks, do not have a single, fixed identity. They live a life of duality. An electron, for instance, can sometimes behave as if it were a tiny, solid, definite particle, like a single grain of sand. But at other times, it behaves as a diffuse and spread out wave of possibility, like a ripple expanding on the surface of a pond. It is not one or the other. It is somehow, mysteriously, both at once. This wave-like nature means that a particle doesn't exist in one single place until it is observed. Instead, it exists in a state known as superposition, which can be imagined as a gentle, shimmering cloud of all its possible locations and states, all existing simultaneously. An electron in an atom is not a tiny planet orbiting a nucleus. It is a standing wave of probability, a cloud of potential that surrounds the nucleus, and the act of measuring it, of looking for it, is what coaxes it to settle, just for a moment, into a single, definite position. This leads to one of the most profound principles of this hidden world, the Heisenberg uncertainty principle. It tells us that there is a fundamental limit to what we can ever know about a particle. The more precisely we know its position, the less precisely we can know its momentum, its path through the world. And the more we know about its momentum, the fuzzier its location becomes. This is not a failure of our measuring instruments. It is a deep and fundamental truth about the nature of reality itself. The universe, at its most basic level, has a gentle, blurry, and uncertain heart. It does not deal in definite certainties, but in tendencies and likelihoods. And perhaps most mysteriously of all, this quantum realm is governed by a strange and intimate connectedness. Two particles can become entangled, linked in a way that transcends space and time. No matter how far apart they are taken, be it across a room or across a galaxy, they remain in a kind of silent communication. A change in the state of one particle is instantaneously reflected in the state of the other. Einstein famously called this spooky action at a distance, and it suggests a deep, holistic unity to the cosmos, a hidden layer of reality where separation is an illusion. The solid, predictable, clockwork world of Newton, and even the fluid, geometric world of Einstein, seems to dissolve at this fundamental level into a shimmering, probabilistic dance, a silent and unseen choreography of potential and connection that underpins all of existence. The universe, it seems, is less like a great machine and more like a great, unfolding thought. From the deep and mysterious uncertainty that lies at the heart of all matter, we now turn our journey inward to the equally mysterious way our own minds construct a world of apparent certainty and continuity from the fleeting moments of our lives. We feel like a single, continuous self, a being that flows seamlessly from yesterday into today and on towards tomorrow. And the thread that stitches this coherent self together is the remarkable faculty of memory. It is the river that flows through our inner landscape, shaping our identity, informing our decisions, and giving our lives a sense of narrative and meaning. But memory is not a simple recording device, a perfect archive of the past stored away in a dusty corner of the brain. It is a living, creative, and profoundly biological process, a constant weaving and reweaving of the connections between the billions of neurons that make up our minds. When we have a new experience, the sight of a sunset, the sound of a loved one's voice, the scent of rain on dry earth, that sensory information is sent to a beautiful, seahorse-shaped structure deep within the brain called the hippocampus. The hippocampus acts as a master weaver, gathering the disparate threads of sight, sound, and emotion from different parts of the brain and binding them together into a single, coherent tapestry, a newly encoded memory. But this memory is not stored within the hippocampus itself. Instead, it is held in the connections between the neurons, a principle known as synaptic plasticity. Imagine our brain as a vast, dense forest with no paths. A new experience is like the first journey through that forest, creating a faint trail. If we repeat the experience, or recall the memory, we walk that path again, and the trail becomes clearer, wider, and easier to travel. In the brain, this happens through a process called long-term potentiation, where the synaptic connection, the tiny gap between two neurons, becomes more efficient. The signal between them becomes stronger. The whisper becomes a clear conversation. Our memories, then, are not things, but pathways, patterns of strengthened connections etched into the very architecture of our brains. And we have different kinds of memory for different kinds of knowledge. There is our explicit memory, the conscious recall of facts and events. This is our autobiography, the story we tell ourselves about who we are. It is the memory of your first day at school, the name of a dear friend, or the details of a cherished holiday. But there is also a deeper, quieter form of memory called implicit memory. This is the unconscious memory of skills and habits, the knowledge of how rather than what. It is the memory that allows you to ride a bicycle without thinking about how to balance. The memory in your fingers that knows how to type or play a piece of music, the comforting and automatic sense of familiarity you feel when you walk into your own home. This silent, bodily wisdom is just as much a part of you as your conscious recollections. And so, the self that you experience yourself to be is not a fixed entity, but a dynamic and ever-changing story, told and retold by the constant, shimmering dance of these neural connections. You are a living river of memory, your present moment constantly enriched by the currents of the past, flowing gently onward into the quiet possibility of the future. The river of memory that flows within our minds gives us a profound and intuitive sense of time's passage, a steady and irreversible current that carries us from the known shores of the past into the unexplored territory of the future. We can remember what we had for breakfast yesterday, but we cannot remember what we will have for lunch tomorrow. A glass can fall from a table and shatter into 1,000 pieces, but we never see the pieces leap back from the floor to reassemble themselves into a perfect glass. In our experience, time has a clear and unambiguous direction, a forward-moving arrow. And yet, when we look at the most fundamental laws of physics that govern the universe, from the elegant dance of gravity to the intricate laws of electromagnetism, we find a strange and beautiful symmetry. These laws would work perfectly well if time were to run backwards. A film of a planet orbiting a star would look just as natural and plausible if it were played in reverse. The fundamental interactions of matter and energy seem to have no preference for the past or the future. So from where does this powerful, all-encompassing arrow of time emerge? The answer, it seems, lies not in the nature of individual particles, but in the collective behavior of the universe as a whole, in a deep and gentle principle known as the second law of thermodynamics. This law tells us about the flow of energy and the tendency of all things to move towards a state of greater probability, a state we call higher entropy. Entropy is often described as a measure of disorder or chaos, but it can be more peacefully imagined as a measure of uniformity, of energy spreading out, of things settling into their most natural and stable state. Imagine a single drop of cream placed gently on the surface of a hot cup of coffee. The initial state, with the cream separate from the coffee, is a state of low entropy. It is ordered and unlikely. But as you watch, the cream naturally and irreversibly begins to swirl and diffuse, spreading itself out until the entire cup is a uniform, milky brown. This final state is one of high entropy. It is a more probable, more settled state. There are simply far more ways for the cream and coffee molecules to be mixed together than there are for them to remain separate. The universe, in its entirety, behaves in the same way. The reason that time moves forward is because the universe itself began in an extraordinarily special, highly ordered, low entropy state. The initial moment of the Big Bang, with all of its matter and energy compressed into a single, smooth, unified point, was a state of near-perfect order. Since that first moment, the entire 14 billion year history of the cosmos has been the story of that initial order, gently and gracefully unfurling, like a closed flower opening its petals to the sun. Every star that shines, every planet that forms, every complex chemical reaction, and every living, breathing organism is a temporary and beautiful eddy in this great, cosmic river that is flowing towards a state of greater entropy. The arrow of time, then, is the sound of the universe exhaling, the whisper of energy spreading out, the gentle and irreversible process of the cosmos settling into the most peaceful and probable version of itself. As we follow this gentle cosmic exhalation to its ultimate and distant conclusion, we journey into the far, far future, into the deep twilight of the universe. The story of our cosmos, driven by the relentless arrow of time, is one of a continuous and graceful unfurling towards a state of perfect and lasting peace. Our current understanding suggests that the universe will continue to expand, its expansion not slowing down, but accelerating, driven by a mysterious influence we call dark energy, which seems to be woven into the very fabric of space itself. Over billions and then trillions of years, this acceleration will pull the great island universes of galaxies further and further apart. A future observer, looking out from our own Milky Way, would one day see the neighboring galaxies recede, their light growing fainter and redder until they slip away entirely over the cosmic horizon, leaving our own galaxy as a solitary island in an endless, empty void. Within this lonely island, the story of the stars will slowly draw to a close. One by one, the great stellar furnaces will exhaust their nuclear fuel. The last, small, red dwarf stars, which sip their hydrogen fuel for trillions of years, will finally flicker and die, becoming cold, dark embers of degenerate matter. The universe will enter what is known as the degenerate era, a cosmos of darkness and silence, populated only by the ghostly remnants of dead stars. Cold white dwarfs, dense neutron stars, and the silent, gravitational wells of black holes. The universe will grow ever colder, its temperature approaching the ultimate cold of absolute zero, the point at which all motion ceases. And as the cosmos cools and darkens, the very structures of matter will slowly begin to dissolve over unimaginable timescales, longer than the current age of the universe, by factors of trillions. Even the protons that form the hearts of atoms are predicted by some theories to eventually decay, and the dead stars themselves will evaporate into a faint mist of subatomic particles. The last bastions of structure and complexity will be the black holes. But even they are not eternal. As Stephen Hawking discovered, black holes themselves radiate a faint, whisper-thin glow of energy, a process now known as Hawking radiation. Over truly astronomical timescales, so vast that our human minds can barely grasp them, even the most supermassive black holes will slowly, gently evaporate, returning their locked-up mass and energy back into the universe as a final, diffuse warmth. Eventually, after the last black hole has faded away, the universe will arrive at its final state. This is the theorized heat death of the cosmos. It is not a fiery end, but a state of ultimate, quiet stillness. It will be a vast, cold, and infinitely expanded space, filled with a uniform, low-energy mist of photons and elementary particles. All processes will have ceased. There will be no more flow of energy, no more change, no more difference between one place and another. And in a universe where nothing happens, the arrow of time itself will lose all meaning. The grand, 14-billion-year story of cosmic evolution, with all its brilliant stars and swirling galaxies and complex life, will have settled into a state of perfect, unending, and silent equilibrium, a final, gentle peace at the very end of time. We have journeyed together across the entire expanse of time, from the silent, pregnant moment before the beginning, to the last, faint and distant whisper of a universe that has finally found its peace. We have witnessed the weaving of starlight, the slow greening of the continents, and the awakening of a mind that could look up at the sky and wonder. It is a story of unimaginable scales, of distances measured in light years, and of time measured in eons. A story so vast it can leave us feeling small and fleeting in its presence. But the deepest truth, the most profound revelation of this entire journey, is that this grand cosmic story is not separate from you. It is not a distant, impersonal spectacle that you are merely observing. You are, in the most literal and beautiful sense, a living, breathing, and conscious part of that story. The atoms that constitute your body are the very same atoms that were forged in the heart of this cosmic drama. Consider the oxygen that at this very moment is filling your lungs with each gentle breath, the element that gives you life and energy. That oxygen was created in the core of a star at least 5 times the mass of our Sun, a star that lived and died long before the Earth was ever formed. The carbon, the versatile and fundamental atom that forms the backbone of every protein and every strand of DNA within you, was fused in the hearts of smaller stars, stars like our Sun, in their final, glowing moments as they swelled into red giants. Think of the calcium that gives strength to your bones, the framework that holds you together. That too was synthesized in the final, intense stages of a massive star's life. And the iron, the element at the center of the hemoglobin molecule that carries oxygen through your blood, giving it its rich red color, was the last element to be created in a star's core before its magnificent, final collapse. Every atom of iron within you represents the end of a star's long and patient work of creation. And all the elements heavier still, the trace amounts of copper or zinc, or the gold in a cherished piece of jewelry, were born in the fleeting, fiery brilliance of a supernova explosion, scattered across the galaxy as a generous gift to the next generation of stars and worlds. This is not poetry or metaphor. It is the simple physical truth. The universe is not something that is out there. You carry it within you. You are stardust. You are the ashes of long-dead suns, given a new and temporary form, animated with the gift of life. And just as you are made of cosmic matter, you are also an expression of cosmic time. The ancient, unbroken chain of life, stretching back nearly 4 billion years to the first simple cells in the primordial ocean, is written in the language of your genes. The deep history of our vertebrate ancestors is echoed in the structure of your spine, and the story of our primate heritage is told by your grasping hands and your forward-facing eyes. And in your mind, in your ability to be aware of this very moment, the universe has developed a way to know itself. After 14 billion years of silent, unthinking evolution, the cosmos has produced a creature that can look back upon the grand journey, that can piece together the story, and that can feel a sense of wonder and awe at its own existence. You are not just in the universe, you are the universe, experiencing itself. And so, here we are. After a journey of 14 billion years, through the birth and death of stars, across the vast and silent oceans of a young world, through the long reign of giants and the quiet flourishing in the shadows, and into the luminous inner sky of the mind itself, we have arrived at the final destination. And that destination is not in the distant past or the far-flung future. It is not in a faraway galaxy or in the heart of an atom. It is here. It is now. It is this single, simple, and profoundly peaceful present moment. Our minds are natural storytellers, constantly weaving the past into the future, but the place where we truly live is in this small, gentle window of awareness that psychologists sometimes call the specious present. It is not an infinitely thin slice of time, but a soft, brief duration of a few seconds, the space in which we experience the unfolding of a musical note, the rhythm of a conversation, or the feeling of a single, conscious breath. This quiet, gentle now is the culmination of everything. The entire grand, cosmic, and evolutionary story we have traveled through has conspired to create this one simple moment of your awareness. The perfect, low-entropy order of the beginning, the generous sacrifice of ancient supernovae, the improbable journey of life, the freeing of the hands, and the awakening of a mind that can know, it has all led to this. To you, resting here, in the stillness of this room, breathing. And so, for these last few moments of our journey together, simply allow your awareness to rest here as well. Feel the gentle rise and fall of your chest with each breath. Notice the quiet sounds of the space around you. Feel the soft weight of your body as it is held and supported. There is nothing else to do. There is nowhere else to be. The grand story has been told, and its ultimate meaning is found in this simple, quiet peace. You are a child of the cosmos, a vessel of stardust, a living echo of deep time, and you have arrived, perfectly and completely, in the sanctuary of this present moment. The entire history of the universe has unfolded to grant you this stillness, this opportunity for rest. So let the story dissolve, let the journey fade, and allow yourself to drift into the quiet, peaceful darkness, into the restorative silence of sleep. Thank you for joining me on this journey through time. If these stories have brought you some small measure of comfort, I hope you will join me again for another journey soon. Until then, may your rest be deep and your dreams be peaceful. Good night.